this section because I want to talk about the concept of cross product, get the idea of it. But we'll focus more on 11.6 today because the cross product is going to be used in some of the stuff we do in there anyways. So we'll get a chance to practice doing the cross product in 11.6. So that'll be more of our focus today, but there's a couple things I want to mention about the cross product. So first off, just to give you a conceptual idea of what's going on with the cross product or why we need this other form of multiplication for vectors, torque is something that we can all relate to. It's the force acting on an object that causes it to rotate. And the object moves around an axis, okay? Think of a wrench, right? When you're trying to tighten a nut, that axis would be the nut, and you use torque to spin it. So basically, we can look at torque as a vector valued quantity. So what we can look at is the force and the distance vectors. So the force would be the force being applied to the lever, and the distance is the distance from the axis of rotation that we're applying the force. It'll make a little bit more sense when I put a diagram up here. But torque depends on those two things, right? Again, this is something we can all relate to. The longer the wrench, the more torque you get. So we got our pivot point, and let's say we're applying a force F. Well, that force F is being applied some distance from the pivot. So that was the distance being referred to. Now, the only thing that's going to rotate this wrench or this lever is the force that's perpendicular to it. Any force that's parallel to it isn't going to move it. So we only care about the component of force that is perpendicular to the lever. So let's give some angle theta. Notice that that perpendicular side is the opposite side. So F perpendicular is basically the magnitude of F sine theta. This is basically our geometric definition of the cross product. So when we're measuring torque, it is the same idea. Two things going on with torque. It has a magnitude and it has a direction, because if we think of screwing in a bolt or a nut, that has a direction, right? It's going into an object. So let's talk about the geometric definition. Again, the idea of torque, just to give you some concept of what we're talking about with cross product. So if we have A and B are two vectors, then a cross B out of the dot. That's how we know which type of multiplication it is. The magnitude is magnitude of A, magnitude of B, sine of theta. Now, just like with the geometric definition of dot product, this is great if we know the angle between the two vectors, which is not always going to be the case. So we're going to like the algebraic definition better, even with cross product, just like with dot product. Now, this is a vector valued quantity, so it has both magnitude and direction. And the direction is going to be perpendicular to the two planes that make the cross product lies in. In other words, for the cross product of A and B, they lie in this plane on the screen. A cross B is either going to be perpendicular out of the screen or perpendicular into the screen, depending on if we do A cross B or B cross A. We're guaranteed it's going to be perpendicular. The only question is it coming out of the screen or going into the screen? And one way of determining that is with the right-hand rule. Now, we only need the right-hand rule if we're using the geometric definition. When we use the algebraic definition, we're going to get a vector as our output. So the direction will be will be inherent in the vector. You don't have to calculate that separately. But the way the right-hand rule works, there's a couple different ways that this is described. But here's basically how the right-hand rule works. You put your forefinger in the direction of the first vector. You put your middle finger in the direction of the second vector. And whichever way your thumb is pointing is the way the cross product is going. So we'd be, you know, if you can imagine A, B, then it's up, right? But if we were to reverse that, A, B, now it's down. Or sorry, B, A, right? B, A, now it'd be down. Another way of that the right-hand rule is sometimes described is you put your fingers in the direction of the first vector, curl them in the direction of the second vector, and whichever way your thumb ends up pointing is your direction of your vector. Because you can imagine A cross B goes this way, but B cross A goes that way. So both of those are fine. It's not going to be something you're going to use a whole lot in here because, again, we're going to use the algebraic definition more often. Specifically, let's get into the algebraic definition. You guys saw this in the video, so I'm not going to spend a ton of time on it. But it's a formula that looks like this. It's a crazy looking formula. For those of you guys who have or are taking linear algebra, this can be done as the determinant of a 3x3 matrix. I'm not going to go over that right now because not everybody needs to know that. Again, for the exam, remember, you're going to have your note cards. So this could be a formula you put on your note cards. I don't want to make memorizing how to do cross product a big part of this class. Knowing when to use cross product is going to be the big part of this class. Okay. So I'm not going to worry about the determinant of a 3x3 matrix, but for those of you guys who are doing linear algebra, that's all that's really being done. All right. Now I do want to point out, you know, what might look like a discrepancy initially between this formula up here and the formula down below, and that is on the middle term. Notice up here it's A3B1 minus A1B3, but down here it's A1B3 minus A3B1. Well, that's because of this negative in front here. That would reverse the order to make it look like this one up here if you distributed the negative. And for those of you guys who have taken a determinant of a 3x3 matrix, you know why that negative is there because you switch signs every time. But I don't want to bog you down with the determinant of a 3x3 matrix if you're not currently in linear algebra. Again, we don't try to memorize that formula, just have it be one that, you know, is on your note card. All right, just a few applications that are kind of interesting. Area of a parallelogram. So if we're looking at A cross B, it turns out it'll find the area of this parallelogram. And the reason may not be obvious at first, but if we think of the height of that parallelogram, right, and that's the same as the h over here, well, that's the opposite side. So we know h equals b, the magnitude of b sine theta. Then we're at our geometric definition because we're going to multiply the base, which is the magnitude of A, times the height, which is the magnitude of B sine theta. There is the geometric definition of our cross product. So the magnitude of the cross product actually gives the area of the parallelogram formed by the two vectors. We don't need to derive that. It's just an interpretation, a geometric interpretation of the cross product. Now, what's really nice, what's nice and follows, I don't know where. All right. What follows from that very nicely is there's also a triangle formed by the two vectors, right? Well, notice that's exactly half of the parallelogram. So cutting that magnitude in half gives the area of the triangle formed by the two vectors. We can extend this a little further. And I think you guys saw this one in the video. If you did A dotted with B cross C, you get a triple scalar product because it ends on a dot product. And that scalar has a geometric meaning too. It's the volume of a parallel pipette, which is this guy here. Now, why this works? Well, actually, I'll show you on the next one. But we know B cross C gives the area of this parallelogram on bottom. Multiplying that by the height of this thing would give the three-dimensional volume. Well, that height is just the vector projection of A in the direction of B cross C. Because we know B cross C has to be perpendicular, just like the height has to be perpendicular to this box. So what we end up doing, we know B cross C gives that yellow area, great. And then A dotted with B cross C gives the vector projection, which is essentially the height. Therefore, that scalar that we get is the volume of this box. So pretty cool, but again, something we might do in a homework problem, but not not our ending point. The biggest thing about the cross product is that it gives us a vector that is parallel to the plane that the two vectors we're cross producting lies in. And we'll talk about in 11.6, one of the applications that'll make this, oh, that's why we do it right away. So just a little comparison of the two. Both operations need two vectors for dot product and cross product. Dot produces a scalar, cross produces a vector. All right, when you do that formula that I showed you for cross product, you get three components of a vector, right? It's not a single number. So be aware of that. Now, if they're both perpendicular, we know dot product is 0, which is huge for us. Well, the cross product is actually at a maximum. That makes sense if we think about torque, right? When are we going to get maximum torque? Well, when we're pushing perpendicular on the lever, right? Dot product, one of its big uses, and you're going to see this a lot in some formulas I'm going to show you in 11.6. It projects one vector in the direction of another. We used it last time to find the shortest distance between a point and a line. The cross product, again, its most important feature is that it finds a vector that is normal to the plane that the two given vectors lie in. Now here's something that's interesting. The dot product, we talked about this last time, generalizes into n dimensions. We did it with 2D vectors and 3D vectors. We could do it with 10D vectors, 1000D vectors if we needed to. Cross product, not so much. It's only confined to 3 space only. So if you're working in 2D, you already know cross product is not going to be something you're going to use. Both vectors involve the lengths of 2 input vectors and the angle between them. One of them uses sine, the other one uses cosine. The only time we really need the geometric definition of them is, again, if we have the angle between them, or like you saw in the worksheet last time, if you're trying to find the angle between 2 vectors, you set the 2 definitions of the dot product equal to each other and solve for theta. In theory, you could do that with cross product too, but I highly recommend you don't for 2 reasons. Number one is you got to do the cross product, which is a more complicated mathematical procedure than the dot product. So there's more opportunities for mistakes. Number 2, using inverse cosine is better because the range of inverse cosine is 0 to pi or 0 to 180. With sine, it's negative pi over 2 to pi over 2. And so you won't necessarily, you'll have to deal with negative angles and think about how those work in relation to the angle between the vectors. So always, 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 if you do an angle between 2 vectors, just put the 2 definitions of dot product equal to each other. Stay away from cross. Can absolutely be done, but you're making more work than you need to. Okay, that's all I really wanted to talk about the cross product. Any questions about cross product before we go on to planes? All right, this is going to be the more interesting section. Not that cross product isn't interesting in its own right. It is, but it's it's a little on the straightforward side. It's like, okay, we calculate cross product. What does it give us? It gives us a vector that has a magnitude and a direction that is perpendicular to the plane that the other two vectors lie. Great. But why do we care about that? Well, let's find some reasons to. All right. There's a couple things I want to talk about with the lines and planes. And just a reminder, like everything that I talk about on these PowerPoints, you have available to you up and more. There's going to be some formulas in this one that we are going to use when we get to the worksheet. So, you know, by all means, take the PowerPoint so you have it with you when you work on some of these problems, because this course is not about memorizing formulas. You're going to have note cards for the exams. Quizzes and homework are open note and resource. What we need to do is know how to use when to use which formula.
Professor, can I ask a question?
All right. Now, something that you would have seen in Calc 2 is parametric equations. So let's first start off by talking about the relationship between parametric equations and vectors.
Professor Clark, can you hear me? Hello?
Oh. Sorry, just saw that we had a question. Sorry, Thomas, what was the question?
Can you hear me? Can you hear me?
I'm getting no sound. Oh, hang on.
Can you hear me now?
Yes.
Awesome. So question, I noticed that the video like lessons are not accessible after the due date. Is that just, why is that? That's such a good resource, and is that for a reason? Is that on accident?
You can still get to them. You have two options. You can either access them through the gradebook, or you can use a late pass. Either or won't affect your score. So you always have access to them.
Okay, gradebook or late pass. And if I've already done them and I use the late pass, it won't affect my original score.
Exactly. Won't have any effect.
Thank you.
Yep. Yep. And I'm happy to give you more if you need more too. Okay. Yeah. Good question, guys. You can always access past assignments through the gradebook or with late passes. Just realize if you access an assignment, this is not so much for the video lessons, but if you access an assignment through the gradebook, if you have not completed it, because it shows the answer, you lose the ability to apply late passes because it shows the answers. So only go through the gradebook on an assignment if you're done working on it. Otherwise, use late passes, and if you run out, just shoot me an email. I'm happy to give more. Okay. All right. 11.6. Let's talk about parametric equations. So right now we're just talking about right now we're just going to talk about parametric equations of a line. So these are just other ways of doing linear functions. You can graph parametric equations in your graphing calculator. You can do it on Desmos. So if you ever want to see what these things look like, there are plenty of ways to plot them. And if you have questions about that, you can ask Professor Tar or myself. But you just need to change your mode to parametric in your calculator, and you can do parametric equations. We're going to look at some very specific things about parametric equations. Number one, this would be in 2D. So not right now, we're in the 2D plane. So this would be parametric equations that go through a point x0, y0, and they have a slope of a in the x direction and b in the y direction. Okay. Now we're used to thinking of slope as rise over run because we're looking at a function. When we're doing parametric equations, we think of each variable as having its own slope. That's a good thing though, because that allows us to relate this very easily to vectors, because those slopes give us the direction in x and the direction in y. Therefore, the vector that is parallel to this line that we're given is AB. And it is that straightforward. You know, we don't have to think about it. We know if we're given a line in parametric, AB is going to be the vector that is parallel with it. That same relationship holds. Oh, and the other thing to mention is if we're thinking about the slope of what this, the slope of this line in 2D, y with respect to x, well, we've got a rise of b and a run of a. So b over a would be the slope of the line as a function. Same thing goes in 3D. We just have another equation now for z. That's what's going to make it go up and down the z-axis. And we will do some really cool stuff later with these parametric equations. Right now, we're just kind of hitting the tip of the iceberg. You're going to get a little bit of practice with them today. And the same thing goes with the vector. Okay, just the slopes in the a, b, or excuse me, x, y, and z directions. So the question I got online is whether or not there should be a preference for what point, beginning or end, should be picked to fill out the parametric equation. It's going to depend on what we're doing. Right now, we're just looking at parametric equations as infinite lines in 2D and 3D. So there's no particular ending and beginning point. But that is going to be something we take into consideration as we go on, is how do we make a line that starts at one point and ends at another point, in which case we would set an interval for t. So if we wanted this to go from x0, y0, z0 to some other point, we might say t equals 0 up to whatever our ending value is. And that is going to be something that we do a little bit of as we move on with parametric equations. Because sometimes we do want them to begin and do a line segment instead of an infinite line. But right now, we're not worried about that in this section. Okay, changing gears a little bit. Linear functions. This is old stuff. In 2D, we've got a slope, change in y over change in x, right? And b gives the y-intercept, and we get the graph of a straight line. So now we need to expand this into 3D. Well, we talked about this a little bit before. A line, something that makes a line in 2D makes a plane in 3D. The only difference now is we have a slope in the x direction and a slope in the y direction. And so what happens is we look at one direction at a time. So if we keep y fixed, and we want to know how z changes, z being the output, right now we're calling it f of xy. How does z change per unit change in x? Well, that's m. So what's nice about this is m is still change in output with respect to input, but just in the x direction. So what we might say, just to kind of, so m gives the change in z value with respect to a change in x holding y constant. And n is the change in z value with respect to a change in y holding x constant. Apologies for my messy writing. So, for instance, we can, we have calcplot 3D. So we come over here, and two ways to do a plane depending on how you have it defined. Right now, we have it defined explicitly for f of xy. So we can just go into z equals and 2x plus 4y minus 2. Nothing too surprising. We get a plane. It hits the z-axis there at -2, which makes sense because of the -2 here. And
we can't see on this end.
really, is it not shared? It was shared.
Like, we see the cow plot 3D, but it was like static.
Oh, really? How about now?
Yeah, we're good now. That's weird.
Been moving?
Yes.
Okay, I don't know why it stopped. Okay, thanks for letting me know. So one of the things, and like I said, we're not going to draw a whole lot of 3D graphs in here. It's really difficult. Planes are incredibly difficult to draw in 3D. If you ever have to draw a plane in 3D, what you do is you find where it intersects each axis and put a point there and just make a triangle. Okay, that'll kind of at least give you an idea of what the plane should look like, because it's impossible to draw a plane in 3D on axes when you're looking at a two-dimensional piece of paper. Like I said, we're not going to have to draw a whole lot of planes, so I don't want you to worry about that too much. But if you ever have to do it, if you're ever doing it for a problem, that's typically what we do, is just mark the axes, intercepts, and then just make a triangle between them. All right. Going back. Okay. So just a couple things I want to look at with the plane, and then we'll talk about some of those formulas that you saw in the lesson, and then we'll get to work on some problems, which is where the really interesting stuff happens. So if you imagine walking on a tilted plane, so imagine that the floor where you're at is tilted. The slope's not always the same unless we set it to be the same. But if you walk in a direction parallel to the x-axis, you'll always be walking the same slope. You walk in a direction parallel to the y-axis, you're always walking the same slope. Those are those m and n from the previous formula. So what's happening that's creating the linear function is the m and n are constant, right? Just like in 2D, the m is constant, now the m and n are constant. And x, y, and z are all to the first power. We're going to see a couple different forms of a plane. And, you know, depending on what we're doing, one form may be more useful than another, but here's kind of a general form. If you wanted, you know, this would be like the point normal, not point normal, excuse me, the point slope form of a line. This would be the point slope form of a plane, because all we need to do is find m and n, and then we can plug in x0, y0, and z0. Okay. Now, here's something I want to show you. This is the table for this linear function. So we know that the graph of this is a plane. It is a linear function in 3D. What kind of observations do you make about this table? What patterns do you notice in the outputs? What's it?
The numbers, if you're going from top to bottom.
Okay, so if we're going down, we notice each of these goes up by 2, right?
If you're going from left to right, it looks like it's subtracting.
Okay, if we go this way, it looks like they're going down 3. Is there anything in the equation that would have told us that without the table? Yeah, check it out. There's the -3 right there. So that tells us as x goes up 1, z goes down 3, right? As we go down, as y goes up 1, the z values go up 2. So that's how those slopes work. Because when we're going right across, we're holding y constant. And when we go down, we're holding x constant. Here's another cool one. What do you notice? Let me get this gobbledygook off here. What do you notice about going diagonal? Yeah. What do you see, Mark?
That's the difference between 3 and 2.
Yep. We had a slope and we had an m of -3 and a y of +2. Add those together, you get -1, and look at the diagonals. down 1, down 1, down 1, down 1. That's that constant rate of change of the linear function in 3D. Those are the kind of patterns we should see.
Making a lot more sense in the videos.
Okay, good. Okay. Now, something we talked about last time, we introduced the concept of the normal vector, right? A normal vector is perpendicular to something. So a normal vector to a plane is perpendicular to the plane. This is going to be a really cool and a really interesting idea, and I'm going to walk you through it. All right, suppose we have some plane. All right, this plane passes through the point X, Y, Z and has a normal vector ABC. Okay, so we know that ABC is perpendicular to our plane. Well, what we're going to do is we're going to pick another point in the plane. So here's what's going on. Something other than red for once. All right, so here's our plane. We have some point P. And we're going to pick another point, let's call it Q, in our plane. Well, what I'm going to do is I'm going to make a vector from, I'm going to do from Q to Q. Let me see, I want to match my notes. Q. Yeah, let's do Q to P. Okay, well, let's think about the components. I think this is going to be the opposite of what I have on my slide, but that's okay. Let's think about the components of Q to P, right? Remember, it's ending minus beginning point. So the components will be X minus X0, Y minus Y0, and Z minus Z0. All right, so that's that. Now, what we know about that vector is it lies in the plane, right? Well, if I put in the normal vector, let's make this stand out. If I put in the normal vector, this is our normal vector here. What do I know about the relationship of N with QP? They have to be perpendicular. Boom. All right, cool. Here's another thing that we know. What do we know about the dot product between N and QP? Based on what you just told me. Louder.
It's 0.
It's 0, right? Because the dot product of two perpendicular vectors must be 0. You guys just uncovered what's called the point normal form of a plane. Like I said, I think I have it backwards. I think I wrote PQ instead of QP, so sorry about that. But what we do is we dot those two together. We know it's equal to 0, and that gives us this guy right here, which is called the point normal form of a plane. Why is this awesome? Because all we need, let me say that again, all we need to find the formula for a plane is the normal vector and a point in the plane. So this is brilliant. We're going to use this often. We don't need to derive the point normal form of a plane anymore. We can just use it. We can say, oh, I've got a normal vector and a point. Boom, there's my plane. It saves a lot of time. So, and I will give you a hint. There's going to be one of the problems on the worksheet that's going to ask you to do that. And it is as easy as it sounds. So that's our point normal form of a plane. Now, let's leverage something that we talked about last time with what we just did. All right, let's talk about a plane in 3 space. This is a fact. This is some basic geometry. Any three non-collinear points make a plane. Now, non-collinear means that they're not all three on the same line. So you have any 2 points is going to lie on the line. If you have a third point not on the line, you can make a plane through those 3 points, right? So the question becomes, how can we determine the unique plane through 3 non-collinear points? Well, what are you thinking? I hear it. Yep. So let's say here's our P, Q, and R. And what we can do is we make 2 vectors. Maybe we make one here and one here, right? Now remember what we just saw in the last slide. We need a normal vector and a point that it goes through, or a point in the plane. We already have 3 points in the plane, so we're good there. How can I get a vector normal to the plane? And my hint is that we made 2 vectors. Think about what we did in the last section. The cross product. The cross product of these 2 vectors will give us a vector that we are guaranteed is perpendicular to the plane that those 2 lie in. That would be our normal vector. We can use any of those 3 points. It doesn't matter which one. And we can put together our point normal form of a plane. All right, so anytime we're given 3 points, as long as they're non-collinear, then we can do the cross product and get a vector that's perpendicular to them. That's our normal vector. And then we do our point normal form of a plane. All right. And like I said, there'll be one on the worksheet like that. That's going to be our opportunity to practice cross products. So like I said, all this stuff really starts coming together. Okay, just a couple of other formulas that are going to come up that you're going to get to use in the worksheet here in a little bit. Again, we're not memorizing formulas. You'll have a note card for those. We just need to know when to use them. We did this last time, distance between a line and a point. That was the last problem we did at the end of class. It's just a dot product. So all we do is we create a vector between the point P and some point on the line. And then we do the dot product with the normal vector as a unit vector. And boom, we've got the distance. That's the exact same thing we did at the end of class last time. We can expand that. The distance between 2 non-parallel lines in 3D. So we find a point P on one line and a point Q on the other. Okay, this is going to be a very similar idea. We don't care that those points aren't lined up. Any point that's easy to find. All we need is a vector between the 2 lines. Then we'll find a vector U parallel to one line and a vector V parallel to the other. We've talked about that before too. Remember at the very beginning, if our lines are given parametrically, we know how to find a vector parallel. Or if we know the slope of the line, we know how to find a vector parallel, right? So again, those are things that are fairly easy for us to do. Once we have those vectors U and V, well, we need a vector that's perpendicular to both of them. What do we use to find a vector that's perpendicular to given vectors? Cross product. Very good. So that's our normal vector. And then we're going to dot that PQ that we created with the unit vector in the normal vector direction. So hopefully you guys are seeing, I know I'm going through these quick, but it's because I'm going to give you time for the worksheet, but hopefully you're seeing how really it's just the same idea applied in different situations, right? All we're doing is a vector projection in the direction of a normal vector. It's just what do we want it to be normal to? In the first case, we needed it normal to the line. Now we need it normal to 2 separate lines, which is why we need the cross product. What if we needed it for a plane? Guys, it's going to be the same idea. If we wanted the distance between a point and a plane, we got some point out in here space, we got some plane, we'll pick any random point in the plane, make a vector between them, that'll be our PQ. And we already know the normal vector of a plane because we just saw the point normal form. So you put your plane into point normal form if it's not already, get your normal vector, and then you dot PQ with the unit vector in the direction of the normal vector. I think what's funny about these slides, even though this were 3 different problems, did you notice how the formula always looked the same? PQ dot n over magnitude of n, PQ dot n over magnitude of n. The only difference in each of these was how we found the normal vector. That's it. And that's, again, that's the part that I want you to focus on, not the formula itself. All right. Angle of intersections. Last thing we're going to talk about, and again, I just want to give you the idea behind these formulas so you kind of understand where they're coming from. So the angle between a line and a plane is pi over 2 minus the angle between the line and the normal vector of the plane. Why pi over 2? Well, remember, this is our normal vector, so it's perpendicular to the plane. So that's our pi over 2. And then, excuse me. And then if we find the angle between the normal vector and the line, call this alpha, well, we would do pi over 2 minus alpha to get theta, right? Because these two have to add up to 90 degrees for pi over 2. So that's why it's saying pi over 2 minus that. And the reason we do that is because it's easy to find the angle between these 2 lines. That's what we were doing last time. Remember, we were finding the angle between 2 vectors. Well, we would know the normal vector because it's just the normal vector of the plane, right? And that's something we're just going to get used to going back and forth from, taking the normal vector, finding a plane, taking the plane and finding its normal vector. We also know how to find a vector that is parallel to this line. So once we have those 2 vectors, then we're just doing the angle between 2 vectors, which is straight out of the dot product section. I think that was 11.4. All right. So not a brand new formula at all, just thinking about it a little differently. Lastly, the angle between 2 planes. Turns out this is going to leverage 11.42, that dot product, those 2 dot product definitions. And here's the thing. The angle between 2 planes is equal to the angle between their normal vectors. So what you would do is you take your 2 planes, find the normal vector for each, and then find the angle between the normal vectors. What's that? Yep, you got it. So I just wanted to go through those formulas because they are going to be part of problems in the worksheet for 11.6. Just to give you a little bit of an idea behind where they come from, because I know sometimes they get introduced and they're not talked about too much. Please, again, I can't stress enough, you're not having to memorize formulas. What I want you focused on is how to use them. All right. Let's work some problems. So we're going to go to the worksheet on 11.6. Like I said, 11.5 is fine if you want to do some extra practice later for cross product, but you probably get plenty in the homework, and you'll get a couple to practice in 11.6. So we're going to focus on 11.6. We'll see how far we get. We might come back together for the last 5 to 10 minutes to look at problem number 9, but depends on how it's going. If you guys are into some good problems, I'd rather have you working on problems because you can always look at 9 later. But let's get you guys working on some problems so you can try some of this stuff we talked about out.